Hello students, we are going to continue with our computer networks class. So this is the Unicast routing protocol. So last thing that we studied was about the longest mask matching, which came after the concept of address aggregation. So now let us move on to the routing protocols that we have. So we will start with Unicast routing protocols. So a routing table can be either static or dynamic. So a static routing table is going to be handled manually. However, in case of dynamic tables, we have to update it with time. Okay. So whenever there is a change somewhere in the network, then it must be the routing table must be updated. Okay. Routing protocols is a combination of rules and procedures that let routers in the internet inform each other of changes. So this routing protocols helps to have the update on the network participants and the various links that are available among the machines. Okay, so these are the various concepts that we are going to learn. So let's move forward. So we have a concept of autonomous systems. So let us try to go deep inside this concept. We can go to the ebook and find out. So here we have Unicast routing protocol. So here we get to see the concept of autonomous systems mentioned here. So today an internet can be so large that one routing protocol cannot handle the task of updating the routing tables of all the routers available in the network. So for this reason, internet is divided into autonomous systems. So the internet that we know about is actually comprised of various combination of networks that work together. So an autonomous system is a group of networks and routers under the authority of a single administration. So it basically means that we have a combination of computers and routers which are going to be controlled or managed by a single administration, and that will be known as the autonomous system. So that means there will be multiple autonomous systems that exist. So routing inside an autonomous system is referred to as intra-domain routing. So all the routing that will happen within a single autonomous system will be termed as intra-domain routing, and routing between different autonomous systems is referred as inter-domain routing. So this is the difference between intra-domain and inter-domain. Okay. So each autonomous system can choose one or more intra-domain routing protocols to handle routing inside an autonomous system. So within an autonomous system, it is basically the control of the administrator, now how he or she would like to have the routing enabled. However, if we consider inter-domain routing protocols, then a proper routing mechanism has to be maintained between autonomous systems. So let us move back to the particular slides. So here you see two intra-domain routing protocols that we will discuss is distant vector and link state, and one inter-domain routing that will be discussed is path vector. So let us go back to the slides. So this is the diagram we have. If we consider one single gray box, it comprises or it represents a single autonomous system. So we can say multiple machines and routers are available here, and then if we combine these autonomous systems, then it becomes the internet. Okay. So each of these autonomous system is going to be governed by a single administrator. Okay. So autonomous itself indicates that sole administration or sole control is enabled. Okay. So this is how things are going to circulate. So if we have a router R1, R2, R3, R4, so it makes the particular actual chain that links all the autonomous systems. Okay. So then considering routing protocols, we already got to know that we have intra-domain and inter-domain routing protocols, and in case of intra we have two, and in case of inter we have one particular example that will be studied. So let us start with the first one, which is distant vector routing table. It is quite simple and straightforward, so please pay attention on this. Suppose we have this particular group of machines. We have A, B, C, D and E. Each of these routers are going to have their own routing tables. For example, A has this information like if A wants to go to A, then it need not cover any distance or does not need to hop through the network, so the cost is 0. And in this example, we consider one single hop as a count of one single hop having a particular cost. Okay, so this particular hop is going to have a cost of say 5, this 2, this 3, this 4, and this 4. Okay, so these values will be placed here. So in a particular routing table, the components that we are going to have are the machines that we have to reach, then the cost associated with a particular path to reach that particular destination, and the next hop that has to be traversed. For example, if we take A, in order to go from A to A, the cost is 0 and we need not go to next hop. Then in order to go from A to B, the cost is 5. Then to go from A to C, the cost is 2. To go from A to D, the cost is E, and to go from A to E, the cost is 6. Here we consider 6 because we consider the shortest path, so 2 and 4 is 6. However, if you take any other path, the length is going to be more. For instance, if you take 5 and 3, it is 8. Then if you take suppose 2, 4 and 3, it is 7, 8, 9. Okay, so all the other values are going to be more than 6, so we consider the minimum value because we want to keep things optimized. Okay, so then we have suppose D. Let us take another example. So in case of D, if it has to reach A, it is going, the length is 3. Then from D to B, the length is 8, because to go from D to B, it has to go via A. So the next hop is A, and the length is 3 plus 5, which is 8. Then to go to C, it is from D to C, the length is 5, because 3 plus 2, and the next hop is going to be A. To go from D to D, it is going to be 0, so it is simply inner loop, so there is no next hop. And to go from D to E, we consider 9. Which one do we take? 4, 5, 6, 7, 8 times. So we take this particular path to go to E, and the next hop from D is going to be A, so we write A here. Okay, so this is the meaning of the values that we see in a particular routing table. Okay, so similarly all the other values are there. So these values are attained after a lot of exchanges of information. So initially, this is in an initial state, this will not be the scenario, it will be something else which is shown here. Okay, so here what do we see? Initially, suppose A has a routing table. So this is the destination nodes, this is the cost associated, and this is the next hop values. So if you look at this particular node A, then it is directly linked with D, C and B. So we have the values 3, 2 and 5, right? So here you can see the values 3, 2 and 5, because A can directly talk with these machines or interact with these machines to get the cost associated with exchanging messages with this particular machines, right? So from A to A, it already knows it is 0. From A to B, it knows it is 5. From A to C, it knows it is 2. And from A to D, it knows it is 3. However, it does not know a path from A to E, and therefore we have a infinite value here. Okay, so we still don't know what has to be done. Okay, so there are no next hop values here till now. Then we go to D. Similarly, from D we can only reach A, that's why we have the value 3, and from D we can go to D in a loop, inner loop, so we have a 0 here. So these two values are known and the other values are unknown. Okay, similarly we go to the C, then we go to A, and then we go to E. So from E to A we don't know yet. From E to B, it is going to be 3. Then from E to C, it is going to be 4. Then okay, the two values are provided here. All right, so and from E to B, we need not have a next hop actually, so you can just keep the convention that is kept in the other tables as well, because we don't see any next hop here. The next hop itself is the destination, so we need not write it, because here see B and B, C and C, right? From E to E it is 0, so the next hop is, I don't know why it's written D here, so you keep this particular column blank as well in case of E. Okay, so let us wind up for now. We will continue in the next video.